Okay, I'm Justin Moll. I'll be talking about, from an enclosure standpoint, some of the thermal and ruggedization challenges that we're seeing. One thing we see in pretty much all the applications is there's always a desire to put more performance in less space. So for us, that typically means that the boards are going to get hotter and hotter, and we need to find a way to cool that and be able to do it in less space and handle all the power and I/O requirements and all that good stuff. So I'll go over a few examples of some of the things that we're seeing, a few case studies, if you will. So in this case, the desire was to have a very small ATR, go to as small as possible ATR, particularly the height of the enclosure. And we started with a, during development, this type of open frame type of chassis, and you can see that there are card guides for conduction cooled boards in there. So the next step was to actually create something that is rugged, meets all the MIL specs for 810, 461, and so on. Another requirement was that it had to be a very secure and reliable connection as well. There were some concerns about previous attempts where it was not going to withstand the rigors of the application. Also price sensitive. This was not, as many of us know in this room, a lot of the Miller applications, price is not the primary concern. This was one where price was something we had to keep in mind. And we had to cool at least 125 watts. Now that isn't a lot in most applications, but when you're talking 3 slots in a very compact space, that's a little bit more. So some of the decision points that we had was, would we do a top-loaded approach, as you see in the bottom picture, or would we do a front or rear loaded? Now the nice thing about doing the front or rear when you have few slots is that you could leverage that height. And one of the requirements was of keeping that height as low as possible because they wanted to put an RF type of device on top of it. So utilizing that space, we were able to do 3 slots with a little space below for some of the I/O, and then you can cable over from the back. Another question was, would there be a dedicated board for the I/O? In a lot of cases, you can have your front panel essentially be a dedicated board, and that board would plug in to the back plane, so you wouldn't have to have all that cabling. But there were concerns from the customer of security and cost and so on in doing that approach. So ultimately, it went to a cabling approach where there wasn't a lot of cables anyway. Another question was, would there be any fans in the system? Of course, when you're adding fans, you're adding cost, you're adding a potential point of failure in there, so there are reliability concerns. And in this case, we found, after some thermal simulations, we found it just wasn't needed. So ultimately, we found that a rear-loaded approach was very effective in getting a very small, compact size, leveraging the minimal height that we could do, and we wouldn't have to go very deep within the chassis. And it was a very secure, since you're going directly out, directly to the panels, it's a very reliable, secure approach. And the result was it passed flight testing and it worked out very well. Another example is a lot of the OpenVPX systems that we're seeing today are using higher and higher power boards. It's not uncommon for slots, a couple slots to be 110, maybe even more watts per slot. and many of the other slots would be probably in that 50 to 75, maybe even 80 watt range. So you're having to dissipate a lot of heat. So in a benign environment for a Mill-Aero customer, we used a recool approach, which I'll talk a little bit more in a second. And worked great, customer is very happy, able to cool very efficiently with RTMs in the back, cool the chassis appropriately, had connections for V267 for RF and so on. But the desire was, okay, well, can we take this into more rugged applications? So some of the decision points were, would we go into, keep it in a rack mount type or to an ATR? And in the recool approach, the advantage of this is we have the fans directly above the card cage. So fans directly above the card cage there. And it's a very powerful, efficient cooling approach, and it pulls the air up and blows the heat 90 degrees out the back. And it's not taking up the space in the RTM, so you could actually have RTMs. Theoretically, you could have 16 slots in the system, assuming 1-inch pitch, and 16 RTMs. Now you'd have to have a little space for wherever you put the power, but theoretically, that's what you can do. So in some cases, we found that if it's a light rugged application, didn't need to meet all the MIL specs, but they wanted a little more ruggedized, we could actually put in some dampeners, a little bit thicker metal, and clamp down the fans so that would meet a certain level of shock and vibration and ruggedization requirements. But the next step was meeting the MIL specs. So one of the options was, and again, we're talking about a very high power system. We're talking about up to 800 watts here. So we found actually in doing some simulation where the boards were placed, it's important of the order that the boards are placed, spacing, the thickness of the walls, thickness of the cold plate, and so on. We found we could actually cool up to 800 watts. So in this approach, it's basically an enclosure within an enclosure. So you have the inside, the inner enclosure, which fully environmental sealed, but then an outside shell that has openings for the fans in the back and on the side to pull supplemental air across those fins to get those fins cooler. Now, when you're also talking about V267 connectors, you need some spacing for standoff for the proper radiuses for the cables and so on, so that's all secure. But ultimately, we found that it is possible. Now, clearly, you're going to go beyond a half ATR, you're going to go wider. But the proof of concept was realized in cooling, going from a rack mount type of chassis to a high power ATR. The other option is to do rugged rack mount. Now, with the RTM connectors, one of the decision points was, would there be just direct cabling to the rear for the I/O or not? Now again, we said that we could do for light rugged, we could use that same type of recool approach. Now if we go to the MIL side, here's where we need to use the MIL grade fans, thicker sheet metal. We could use the same rails because they're already very ruggedized. Put in dampeners and so on, other things that are required to meet the application. So this is actually a little bit different configuration, but ultimately showed that between either going to an ATR or a rugged rack mount, it was possible to go to either of those types for the for higher level ruggedizations for the customer's requirement. Third challenge was a customer had two 6U boards and one 3U board. and wanted to put that in the system. Now we have this type of chassis here that you can see that the 6U segment is actually split up into 2 3U segments. It's a very modular approach, so we can put in dividers to split a 6U into 2 3Us. Now theoretically, we can just put that in one of the slots and then have other 2 slots be 6U, but then we have this giant chassis, this giant 9U chassis that's heavier, really big, and we're wasting all that space just for a few slots. So we went to a horizontal mount approach. Now horizontal mount approaches aren't new, but typically in compact PCI and VME, they were usually side-to-side cooling, and this was an application that needed front-to-rear cooling. And plus, between VPX and those other architectures, there's a little offset in the spacing, so there's considerations for your card guides, for your thread inserts, and so on, to make VPX work, essentially. So some of the decision points that had to be made, although this could be done in 1U, depending on the size of the boards that were put in, would it be better just to do 2U and have that flexibility if they are 1-inch pitch? And how would we mix and match to 3U and 6U? One thing that's nice about the horizontal approach is there is enough space to have a 6U board next to a 3U board, so you could leverage that the space across. So ultimately, we went to the slim box approach with the cards loaded in the rear. And the reason for that is the customer, they had all the cabling in the back of the chassis. So actually we had the the fans in the front, easy for me to say, in front of the chassis, and pushing the air across both the 6U segment and the 3U segment. And of course, there are modular extrusions where it's easy to go from 3U to 6U and make those changes. And ultimately, doing thermal simulation, we were able to prove out adequate cooling for the requirement. So ultimately, we were able to go from a very large chassis to something that's very small, in VPX, front to rear cooled, and customer is very happy. Finally, there are also cases where we're starting with a commercial device that's already out in the field, and they want to make it more rugged. So some of the requirements for this was, one, make it weatherproof. Now in this case, if it meets IP67, it means it has to actually stand in water for a certain period of time. They also wanted options to go to meet the MIL-spec, so to meet the shock and vibration and other specs for military applications. Of course, include conduction cooling and have various mounting options. So one of the decision points was, well, how rugged do we go? We had a little bit of trade-offs here. If it's IP67, then being able to modify the I/O is very challenging. We wouldn't be able to have that flexibility to be able to change the I/O in the front for different applications. Also, if we do a MIL rugged version, then the only certain amount of FPGAs and configurations that we can cool properly. So ultimately, what was decided was we'd start with the most rugged. So here, the design met IP67 for waterproof, meets the MIL specs, fully conduction cooled, and so on. Now, for other applications, there were customers who were looking for something that were for agriculture and other things that didn't need all the ruggedization. In that case, we're able to use aluminum case with fan filtering which is a little bit more rugged but wouldn't have all the other features. But ultimately, we're able to find that we could develop various options with flexibility in the I/O and the FPGAs used, going in various tiers of ruggedization. So to recap, we have design requirements for very small, very compact, very high power VPX, where we need to cool a tremendous amount of heat in VPX. Others where we kind of need to mix and match 3U and 6U and do it in a small horizontal design. And another case where we're doing fully custom IP67 type of solutions. And that's it. Are there any questions?